Thank you for tuning to my talk. I'm Ahmed Saeed, a postdoc at MIT, and this talk is about my work on Annulus, a dual congestion control loop scheme for data center and WAN traffic aggregates. This work was done in collaboration with my colleagues at MIT, AT&T, Sambanova, Intel, Georgia Tech, MPI, and Google. This talk overlaps with a more detailed talk available online. The overlap is just enough to get you familiar with our paper. Then I'll answer the 3 most frequently asked questions about Annulus. Let me start by providing some context. Cloud service providers are investing in high-capacity WANs to connect the data centers. For example, this picture shows some of the links comprising Google's WAN. The rates on the links show how rapidly the network has been growing. The growth in infrastructure is motivated by the exponential growth in traffic demand. This figure shows one of the results reported by Google in the B4 paper a couple of years ago. The figure shows that WAN traffic demand increased by 100x over the period of 5 years. To adapt to this growth, it is now common for modern WAN links to have similar capacity to Intra data center links. So what does that imply? It implies that it's now typical in a data center to have the same rack or even the same machine sending high bandwidth data center traffic as well as high bandwidth WAN traffic. The WAN traffic we're considering here is not the user-facing WAN traffic that's bottlenecked in the wireless network near the user. Rather, these are high bandwidth flows carrying large volumes of traffic between 2 data centers. Consider a backup application across multiple data centers. The congestion control algorithm used by a flow is determined by the sender using a flag that's based on the destination of the flow. WAN traffic uses WAN congestion control algorithms, and data center traffic uses data center congestion control algorithms. For the past decade, we've been developing WAN and data center congestion control algorithms separately, and we've been doing this for good reasons considering the differences between the 2 networks. On one side, data center networks have short RTTs and shallow buffers. They introduce their unique set of challenges like incast, and they also offer some homogeneity and provide the operator with full control over all network elements. This provides flexibility in deploying and experimenting with new algorithms. Significant progress has been made starting from DC-TCP to DC-QCN and Timely, and more recently HPCC and Swift. On the other hand, WANs have long RTTs on high bandwidth demand. They have a mix of deep and shallow buffers. Also, aside from private WANs, deployment of new WAN congestion control algorithms have to take into account the heterogeneity of such networks. This includes competing with legacy congestion control algorithms. Recent proposals for WAN congestion control include protocols like DDR, PCC, COPA, and Nimbus. In this talk, we're concerned with bottlenecks shared between WAN and data center traffic, given that each type of traffic is using its own congestion control algorithm. In order to explore this interaction, we looked at traffic traces collected from some of Google's clusters. We correlate the behavior of WAN and data center traffic. The data I'm showing now is from one such cluster. The data was collected over the period of 2 days. The top figure shows the total throughput of WAN traffic exiting the cluster. The bottom figure shows the median, the 95th percentile, and the 99th percentile latency of all data center traffic in the cluster. The highlighted areas show that as WAN traffic demand increases, the tail latency of data center traffic more than doubles. We also examined the drop rate at Tor switches, which is the first point of oversubscription in the networks that we've studied. We see that the drop rate trends also follow WAN demand. This means that WAN demand can significantly impact and degrade the performance of data center traffic. This behavior is consistent across different clusters and across different time periods. The punchline of our finding is that WAN traffic reaction to congestion is too slow compared to the fast dynamics of data center traffic. This statement might seem obvious, but some of its implications are subtle and result in performance degradation for both WAN and data center traffic. You can refer to the longer video and the paper for a more detailed explanation of the implications of this observation. Now I'll introduce our scheme, Annulus, which achieves near ideal performance for WAN and data center traffic when they compete for bandwidth at the same bottleneck. Our work on Annulus answers 2 questions. The first question is, how do we efficiently manage bottlenecks where data center and WAN traffic compete? The second question is, how do we answer the first question while still efficiently handling other types of bottlenecks? Our main idea to answer the first question is to tackle the root cause of performance impairments when data center and WAN traffic compete. That is the slow reaction time of WAN traffic. We do this by reducing its reaction time through fast feedback. We answer the second question leveraging existing algorithms. More concretely, Annulus is a dual congestion control loop scheme. The first control loop addresses traditional types of congestion by relying on existing congestion control algorithms. WAN congestion control is used for WAN flows, and data center congestion control is used for data center flows. Analysts adds a second control loop that we call the near source control loop. It reacts to bottlenecks shared between WAN and data center traffic. Specifically, when congestion occurs, the bottleneck switch generates an explicit direct message that's sent to the source of the traffic, and the near source control loop reacts to it. Analysts fits in current stacks as follows. Current stacks already have congestion control algorithms for WAN and data center traffic. Those algorithms annotate packets with a pacing rate based on some congestion signal that's piggybacked on acknowledgements. Analysts adds a near source control loop. The near source control loop reacts to explicit notifications from the near source congested switch, and then annotates packets with another pacing rate based on its calculations. The rate limiter applies the minimum pacing rate, reacting to the most congested bottleneck. I refer you to the paper or the longer video for more details on Analysts and our results. Now I'll move to the FAQs. The first question is, why not simply isolate WAN and data center traffic at the switch? To answer this question, we consider the approach of dedicating buffer space to the different types of traffic. Aside from the waste of dedicating an already scarce resource, isolation is not a panacea. While it can help improve the performance of data center traffic, it does not solve the problems faced by WAN traffic, and that is for two reasons. First, there simply isn't enough buffer space in a data center switch to absorb a WAN BDP. Recall that we're concerned here with high bandwidth WAN flows capable of utilizing terabits per second of capacity in aggregate. This means that WAN traffic can consume the whole memory of a shallow buffered switch. This means that isolation will lead to excessive drops when the available bandwidth to WAN flows decrease due to competition with data center traffic. This is made worse by the fact that WAN traffic will still share bandwidth with data center traffic. This means that the available bandwidth to WAN traffic can change hundreds of times within a single WAN RTT due to the fast fluctuations in data center bandwidth demand. This exacerbates the issue of packet dropping caused by lack of buffer space. This figure shows the results from our simulations. It shows the normalized tail latency of data center traffic and the normalized average WAN throughput. It compares ideal performance and the performance when both types of traffic are isolated. While data center traffic can achieve near ideal performance, WAN throughput suffers. I refer you to the paper for more details. The second question is, what about near receiver bottlenecks? The short answer is that Annulus targets near source bottlenecks only and does not handle bottlenecks near the receiver. The longer answer is that the main idea of Annulus is to cut the feedback delay of WAN traffic by delivering congestion feedback directly from the bottleneck switch to the traffic source. This does not apply for near receiver bottlenecks, as the feedback delay is still around an RTT. The reason behind the scope of Analysts is that the near source bottlenecks were the more pressing problem in the use cases we've observed in practice. Of course, near receiver bottlenecks exist, and addressing them would require a different approach than Analysts. I discussed such an approach in the detailed talk available online. The third question is, how did we design the near source control loop, or how did we make the design choices that led to Analysts? To answer that question, I'll first give an overview of how the near source control loop works. On queue buildup, a data center switch generates a direct congestion notification message that is routed to the sender. The message indicates the problematic flow and the extent of the congestion. The sender modulates the transmission rate of the problematic flow based on the congestion level conveyed in the congestion notification message. As you can see, this design is fairly generic. Its key requirement is that the congestion feedback has to be delivered directly from the bottleneck switch to the traffic source. You can probably think of many ways to realize this design. For example, the near source control loop can behave like HPCC if telemetry information is delivered directly from the bottleneck switch to the traffic source. However, our implementation of Analysts is based in practicality. We rely on the QCN standard, which is already implemented in deployed hardware switches. QCN provides the direct signaling we need for the near source control loop. In conclusion, in this work, we identified a new problem in data center congestion control which arises when high bandwidth WAN traffic competes with data center traffic. We also introduced a new congestion control scheme to handle it. Analysts makes the case for developing better direct signals that reduce the reaction time and improve the performance of WAN traffic when handling congestion inside the data center network. We also believe that Analysts should motivate multi-control loop congestion control algorithms to handle scenarios where a flow goes through significantly different types of bottlenecks. Thank you, and I'll take any questions.
Thank you, Ahmad. So while I wait for questions from people, actually now there's a question. So Anna is curious about that Annulus sounds conceptually similar to the multi-domain congestion controls suggested for mobile networks, where people use double control loops and fast feedback from the base station. What are the key differences between the two scenarios? And feel free to say that, okay, mobile networks are very different, but Anna's curious.
So my understanding of how these proxy-based congestion control algorithms work is that they rely on connection termination. And you can correct me if I'm wrong on this. But the key difference between Annulus and such approaches that rely on connection termination is that Annulus does not terminate the connection. The edits are all made still at the source. You can the feedback loop. We just add another feedback loop at the source. So that's the main difference.
So another question coming from Tong Lee is that there is a mechanism called TCP splitting. Why is it that we can't use TCP splitting?
So I think that's a very good question, and that's related to this. I think to the previous question. Any splitting or any division of state of the connection is not really feasible within these small timescales. Also, it's not feasible within the very short latency architectures of data center networks. Just think about the topology of a data center network, and adding such middle boxes somewhere in the topology will just require rethinking the topology and rethinking how we keep that latency short. So we just wanted so the main idea for Annulus is to try to keep the latency in the data center as short as possible, while only augmenting existing solutions, not changing the topology, not changing the hardware too much.
Good. There's a very recent question, and I'm trying to parse it, but let me read it verbatim. So the question is, how can you determine in the causality between high WAN throughput and intra data center latency? I mean, high correlation between them sometimes can be misleading.
So this is a great question, and this is actually why the first iteration of this paper was rejected last year. Exact same question. And the whole section 2 of the paper is dedicated for this. So if you want the detailed answer, you can just read that section. I'll give you sort of the punchline, and that is there are actually 3 reasons for that, for causality, not just correlation. The first one is that there's not enough buffer space for a WAN BDP inside a data center switch, and that's sort of natural even for private WANs. They still use merchant silicon switches. But what makes data center networks a special case is that the data center traffic, and that's the second reason, the data center traffic changes the available bandwidth for WAN traffic at very high frequencies. So consider the flow completion times we target with congestion control algorithms for data centers. It's an order of microseconds, and that's very small compared to a WAN RTT. This means that once a WAN flow stays at a certain throughput, that available throughput can decrease suddenly, and all of those packets have to be buffered somewhere, and there's not enough buffer space for that. And we have a lot of simulations where we try to isolate the two types, the two traffic, or the 2 types of traffic, where we try different congestion control algorithms, we try different congestion control signals. The problem doesn't go away. So it's not really about a certain setting or a certain type of algorithm. It's really a fundamental problem that only happens when high bandwidth WAN traffic competes with data center traffic.
Thank you, Ahmed. That was very interesting. So we have a couple of questions coming on Slack. So I'll just sort of straight away start with asking those. So the first question is, does Annulus require switch modifications?
So Annulus requires switch support, but our implementation of Annulus relies on QCN, which is already implemented in commodity switches. So we didn't really need to change anything about deployed switches. But if we need to make the signal more expressive, or we need to change the logic of the near source control loop, then that might require modification to the switch.
Okay, thanks. And the next question is, how about using a credit-based congestion control algorithm to control both data center and WAN traffic? And then you wouldn't need to worry about feedback latency.
Well, my understanding of credit-based system is that it still will require some information arriving from the receiver to the sender, and that will take that will still arrive at a fairly large RTT. Yeah, so that I think that does not necessarily solve the problem.
Yeah. Okay. Then, so another question is a follow-up question. The first one is, we're curious if QCN is supported on deep buffered multi-ASIC chassis switches.
I don't have an answer for this. I know that some of Broadcom switches support this, support QCM by default, but I'm not sure like if that support is available on deep buffer switches. QCN is specifically for data center switches, so I'm not sure if like typically deep buffer switches will be available for like WAN settings. So I'm not sure if they will support such protocol, but it's a standard protocol, so it's not weird. Like it's not uncommon for switches support.
Okay. So I think there's another question coming up, but in the meantime, I had a question. So you mentioned how like strict isolation between WAN and data center switches, data center traffic is not a good idea because you don't have enough buffer capacity. But let's say that you had like some scheme that could sort of share the buffer space across different priority levels or different queues, and you could still do like some sort of a round robin between the two traffic. So if you don't have any data center traffic, the WAN traffic could occupy all of the buffer space. And if you do have some data center traffic, it would just occupy the remaining space in the buffer, and you could still do round robin between those. Then would the issue of bad interaction between the two go away? Or
so that's a great question, and the answer is no. The problem will persist. And the main reason for why the problem persists is that it's not only about sharing the buffer space, it's also about sharing bandwidth. So when the problem happens when data center traffic, the data center traffic pretty much changes its demand within data center RTT. So this means that within a single WAN RTT, the available bandwidth to the WAN flow can change hundreds of times. And that means that you get these like large bursts of WAN bytes piling up in the data center switch when the data center demand increases. And no matter how much buffer you have in the data center switch, it's not enough to absorb the WAN BDP. Like the only case where the need for Annulus goes away if we have like very large buffers in data center switches. Then just like sort of clever scheduling at the switch like solve the problem.
Okay, great. So another question is, they're just thinking out loud, is whether combining PBE with Annulus would provide better sending rate estimation. So PBE is the first talk where they use like sort of, yeah.
So this is a great question. So I think this is, there is probably some interesting research questions there where, and this is sort of the last conclusion I had in the talk, where I think if a single flow is going to significantly different types of bottlenecks, we might need actually like not just dual control loop schemes, but multi-control loop schemes where each control loop gets its own feedback and sets a rate based on the bottlenecks that it's worried about or it's focusing on, and then the sender will just pick the smallest rate according to that feedback. And I think there are some interesting questions about stability and some guarantees about fairness when thinking about these types of multi-control loop schemes. So I think that's a very interesting point to look into in the future.
Great, thanks. So I think we can continue over Slack. So thank you, Ahmed. It's very interesting work, and I think we can move over to the